What is up, guys? I am back, like I never left, right? Um, this one's right here is a long time coming. I have recorded some parts of this video like a few weeks ago, and here's Garfield. You want to say hi? Want to say hi, homie? He's probably hungry right now. That's why he's not talking. But anyway, this video is about geometric sequence and series. Let's just jump right into it. To kick things off about geometric sequence, let us first define what a geometric sequence is. Basically, a geometric sequence is a sequence where the ratio of successive terms is always the same non-zero number. And this non-zero number is called a common ratio. And now you might be wondering, why are we using the word ratio? To put this into perspective, we can have examples like 1, 2, 4, 8, 16, 1, 3, 9, 27, 81. So as you can notice for the first example, the pattern there is that you multiply by 2 to get the next term. The second example, you multiply by 3. Those are positive integers, they're whole numbers. And also in the geometric sequence concept, we can have negative integers as a common ratio. But in particular, the reason why we use the word common ratio is because in this example, we actually maximize the use of fractions as a pattern, something that we use in a pattern. So we have examples later where we will have a common ratio that is 1 half or zero point 0.5, 1/4 or 0.25, and so on and so forth. So this will make much more sense as we move forward. So first, let's have this example right here. The example 5, 15, 45, 135, and then 405, we can notice that if you multiply 5 by 3, you get 15. When you have 15, you multiply that by 3, you get 45. 45, you multiply that to 3, you get 135. Then if you multiply 135 to 3, you get 405. I was almost going to say 40, 45, and then that doesn't make sense. So it's 405. So basically, the one that we're indicating here, or putting into notice, is the common ratio, which is equal to 3. Okay, so how do we actually get the common ratio other than using our mathematics skills in order to figure it out, like, oh, this is by multiplication or something like that? So the safest way in order for us to get the common ratio is actually by division. So in this case, what we can do to get the common ratio represented by the variable r is to choose any term other than the first term, because there's nothing before it. Okay, so basically we choose any term starting from the second term and then divide it by the one preceding it. The preceding term meaning from the word pre, that's before. So for example, we have here 15 and we divide that by 5. That's the number preceding 15. So in this case, 15 divided by 5 is equal to 3. So therefore, it's correct. Next, we can also have 45, and the one before it is 15 also. And if you divide this is also equal to 3. 135, divide that by 45. The answer is also 3. And if you continue with this one, 405 divided by 135, the answer is also 3. Hence the word common ratio. So again, just like in arithmetic sequence, the pattern must be consistent. Okay? Marami nang hindi consistent sa buhay natin. Dapat ito consistent. Okay? Common ratio. Now let's have some more examples. So let's say we have negative 3, 6, negative 12, then 24. So again, what we have to do here is to get the common ratio first. So we can have 6 divided by negative 3, negative 12 divided by 6, and then we have 24 divided by negative 12. Now, as you can notice here, we are dividing integers of different signs. Always remember, when dividing and multiplying integers of different signs, the answer must always be negative. And as you can notice, the pattern that we have here, from one term to the next, it's changing signs. Therefore, we know here, or it should be assigned to us, that the sign of the common ratio should be negative. So 6 divided by negative 3, that's negative 2. And also negative 12 divided by 6, that's negative 2. 24 divided by negative 12, that's also negative 2. So that is our common ratio. So to get the next one, all we have to do here is to multiply. So let's have 24 times negative 2 to get the next one. And then the answer here is equal to negative 48. So if you continue here, negative 48 times negative 2, negative times negative, again, the rule that I mentioned earlier, we're going to have a positive number, and that would be 96. Then 96 times negative 2, this will give us a negative number, which is negative 192. So in here, we are able to find not only the common ratio, but also the next three terms of the given sequence. So let's have some more examples. We have here 32, 16, 8, and 4. So again, to find the common ratio, so let's start with the second term divided by the first term. We can also have the third term divided by the second term. Then the fourth divided by the third. So as you can notice here, class, the numerator is lower than the denominator. This is where we will actually see a fraction. 16 over 32, that is 1 half. 8 over 16, that's 1 half. 4 over 8, that's also 1 half. Now again, I want to say this, because in this concept, we're actually going to maximize the use of your calculators, especially once the formula is presented. All you have to do here is to decide which one is best for you. My suggestion, if you have 1 half, it's flexible. You can have either 1 half or zero point 0.5. Both will work to your favors. There's nothing wrong with it. But if your fraction is like 1/3, 1 over 7, it's going to be a repeating decimal. This is one of the things that I would like to say. It's not like a rule in mathematics, but as much as possible for us to get the exact values or with pinpoint precision for the final answers, we only do estimation or rounding off in the final answer part. I don't want it, or I don't like it when I round off in the middle. So as much as possible, if you're going to use decimals, it's for exact values like 0.5, 0.25. But if it's a repeating decimal, just stick to the fractions. I hope that makes sense. So in here, we can actually solve for the next terms, like can have 4 times zero point 0.5. The answer here is 2.0, so that's 2. And also have 2 times zero point 0.5, it's going to give us 1.0 or simply 1. Then if you have 1 times zero point 0.5, that's 0.5. And again, do not be confused here. You can also have, again, the terms multiplied by 1 half. 4 times 1 half, that's 4 over 2, it's equal to 2. 2 times 1 half, that's 2 over 2, that's equal to 1. Then 1 times 1 half, that's equal to 1 half. And 1 half in decimals is 0.5. So either way, no matter what you do, it's going to be the same value. Okay, let's have another one right here. We have 768 negative 192. So let's have negative 192 divided by 768. 48 divided by negative 192. Negative 12 divided by 48. As you can notice again, the numerator compared to the denominator, the absolute value, the bigger one, is the one in the denominator. So we're going to have a fraction here. This one is going to be negative 1 over 4. And again, you can write this as negative 1/4. It's still the same. Okay? Please know that when there's a negative sign next to a fraction, when you compute for it or when you solve for it, it's much easier if you put the negative sign in the numerator. Always remember, there's no such thing as a negative denominator, okay? Based on real life concepts, is how can a part be negative, okay? So that's a concept with it. So we're using this because this can also be a decimal, negative 0.25. Any of these three will serve as your common ratio. They will all work. So let's have negative 12. I'll multiply this to negative 1/4. This will give us positive 3. Then we have 3 times negative 1/4. This will give us negative 3 over 4. Now negative 3 over 4 times negative 1/4. Always remember the rule. We multiply the numerators. Negative 3 times negative 1. That's positive 3. 4 times 4. Am I correct so far? Yes. We're going to get 16. So it's 3 over 16. I hope I'm correct with this one. Okay, I think that's it. So let's continue with some more examples. Now, what if we have the first term here? So just to make this quick, we have 7, multiply that to 3, we get 21. Okay, anyway, that's corny. 21 times 3, you get 63. 63 times 3, you get 189. Yep, I think I'm still correct with that. Times 3, okay. Wait, I don't have a calculator with me. I'm doing this mental. 18, 36, 54, 567. Okay. I have a weird way with multiplication in my head. Okay, I'm so sorry with that. But this is your answer here. Now, if we continue, we can have 9 and then negative 2. So we start with 9 as your first term times negative 2, that's negative 18, times negative 2, that's positive 36, times negative 2, negative 72, times negative 2, we get positive 144. Let's just verify if it's correct. Okay, it's correct. So again, just simply multiply it. It's a common ratio. You don't have to overthink it. The more you overthink the concept, the harder it will be for you. But always remember, you're just multiplying anyway. What I think is going to be a problem is if you forget the sign. So you have to take note if it's positive or negative. You have to be careful with that. I think we have one more. Okay, 100 times 1 half. So we start with 100 times 1 half, you get 50. 50 times 1 half, you get 25. 25 times 1 half, that's 25 over 2. If you want to simplify that, this is 12.5. Yep. Then 25 over 2 times 1 half, that's 25 over 4, or 6.25. Yep, 6.25. So you can have either the decimal or the fraction, your choice, pick your poison. So that's how it works. Now, after defining geometric sequence, our next target is to determine if a given sequence is actually geometric. So in this case, how do we find that out? So we have to double check it carefully. So for example, here we have 2, 6, 18, 54, 162. You can already notice that it's similar to the examples we had earlier. 6 divided by 2, you get 3. 18 divided by 6, you get 3. 54 divided by 18, you get 3. So again, if you're confused, you may write it down. Like 6 divided by 2, this is equal to 3. 18 divided by 6, this is equal to 3. 54 divided by 18, this is equal to 3. And same with 162 divided by 54, this is equal to 3. So that's our common ratio, and it is a geometric sequence. Next, how about negative 1, negative 2? You can try it out. Negative 2 divided by negative 1, that's positive 2. Negative 4 divided by negative 2, that's positive 2. Negative 8 divided by negative 4, that's also positive 2. So that's our common ratio. So yes, sir. How about the next one? 3 divided by 1, you get 3. Then 6 divided by 3, you get 2. So here you can notice it's 3, it's 2, it's not common, so therefore it's a no. So for those who might be phasing out, what's happening here? Basically, for us to check, again, this is the careful way of solving this. If you can do it mentally, or you can use your calculators, but if you want to be sure, you can write it down this way. Check it one by one. So you start by looking at the second term, divide it by the first term. Go to the third term, divide it by the second term, to see if there is indeed a common ratio. So in this case, we can notice that the pattern in the third example is different. So it's not geometric. Let's have another one. 2, 4, 6, 8, 10. I think we don't have to divide this anymore. We can easily notice that it's increasing by 2. So therefore, this is not geometric. This one is actually arithmetic. Now, how about for the fifth example, n plus 4, or n is equal to 1, 2, 3, 4. What you have to do here is simple. You simply have to substitute. So you have the n plus 4. This could be, the first one is 1 plus 4. You get 5. Where did we get the n being 1? It's here. So how about if it's n equal 2. So that's 2 plus 4, that's equal to 6. And then how about n being 3? You will have 3 plus 4 is equal to 7. And I think here we can stop immediately because the results can immediately show us that the pattern is not geometric. It's simply increasing by 1. And that's the common difference. This is actually arithmetic. So another no for this one. Now, how about for the last example, 7 raised to n? So 7 raised to n, basically the exponent is the one that we're going to change. So our first example could be 7 raised to 1, that's equal to 7. 7 raised to 2, that's equal to 49. 7 raised to 3, that's equal to, wait, 28, 343. Then 7 raised to 4, wait. Wait, my skills are, is this 2401? 2401. 7 times 3, 21. 2, 28, 3. Yep, it's 2401. So the pattern here is actually the base because it's exponential. So 7 raised to 1, 7 raised to 2, 7 raised to 3, 7 raised to 4. This is actually the pattern, which is 7. The common ratio here is actually 7. Sorry if the colors are changing all the time. Please forgive me with that. The common ratio here is 7. So it's a geometric sequence. Now that we're done with determining if a given sequence is geometric, and as you can notice with the non-examples, most of the non-examples given here, not all, most, especially these two, are examples of arithmetic. So what we're going to do is we're going to compare the difference between the two. That's our next target, is to differentiate what makes a geometric and what makes an arithmetic sequence. So when we're talking about arithmetic sequence, is that it's basically addition. So I would like to clarify what I said before. It's not subtracting. Basically, we're adding whether a positive or a negative pattern, a negative number in this case. Now, that's our common difference. Now, for geometric sequence, we multiply. We do not divide. I would like to clarify that. Again, there are only two operations involved. Arithmetic sequence, we add. Geometric, we multiply. Okay? Remember, for arithmetic sequence, it's common difference. For geometric sequence, it is common ratio. That's why we use the color coding here so that you can see it. In terms of its graph, which will be applied in your performance task, arithmetic is basically a linear change. It's similar to linear equations. That's an arithmetic sequence. And for geometric, it's exponential change, as I have mentioned earlier in the previous example. As you can see here, the way the graph looks like, the way the points are plotted, you can see that in arithmetic, it's straight. You can draw a straight line. While for geometric, it can either be straight up like that, but with no sense of being straight. Some cases, it can actually go down and up. That's the case when we have a negative common ratio. We either go up or down. So that's the case there. Now let's continue. Let's have some examples. So let's try to classify if it's an arithmetic sequence or geometric. So for example, we have 4, 8, 12, 16. Now in this case, you can notice already that the common difference here is positive 4. So that is the common difference. We use letter D again for common difference. So this is arithmetic sequence. You have 4, 8, 16, 32. As you can notice, the first two examples are somewhat similar with the way they began. But the process here, as you can notice, if you divide 8 by 4, you get 2. 16 by 8, you get 2. 32 divided by 16, you get 2. So that's actually the common ratio here, which is 2. This is a geometric sequence. Now, how about for number 3 or the third example? We have 5, negative 5, 5, negative 5. It's kind of goofy, I know, but basically, as you can notice, it's just changing signs. Basically, the reason behind that is because the common ratio is none other than negative 1. That's geometric. I think the ice cream that I ate is now coming back to haunt me. Anyway, let's go with another example, another set of examples. Now I'm stuttering. So you have negative 7, it became 3, 3 became 13, then 13 became 23. The pattern here is plus 10, and plus 10. This is common difference 10 arithmetic sequence. Now here we have n became 3n, 3n became 5n, 5n became 7n. The pattern here is that we add 2n. Now I want to clarify this, class. If you're seeing a pattern like this with a variable and, again, take note, the numerical coefficient, or in simpler terms, the number before the variable is changing, it's basically addition. Okay, if you see a pattern like this, it's addition. This one is arithmetic. The pattern, again, common difference is 2n, and the difference between the second to the last example and the last one, here what changes is the exponent. So when do we have, or what's the case of exponents changing? That's when you multiply. So the pattern here, if you can notice, x squared divided by x, that's x. X raised to 3 divided by x squared, that's x. X raised to 4 divided by x raised to 3, that is x. This is a geometric sequence and the common ratio is x. Okay, so please take note about this. When you can notice that the change is within the exponents or with the exponents, that's probably, again, the word is probably, a geometric sequence. But if the change in the pattern is in line with the numerical coefficient, there's a huge chance that it is arithmetic. The reason why I'm using those kinds of words, because not all the time will it be an automatic arithmetic or geometric sequence. It could have a different pattern, like could be plus 2n, plus 3n, plus 4n, or it could be, this case, a constant 2n, a common 2n. That's why I'm not generalizing things. It's important not to generalize things all the time. There are some outliers with things. That's why sometimes, it's important to ratio your x's. That doesn't make sense. Let's go to the next one, shall we? So the next one here is, we'll try to find the nth term of a geometric sequence. In this case, it's important to take note that here we're going to apply the formula for the geometric sequence, and at the same time we will try to find the general formula for the general term, the formula for the general term. That's what I'm trying to say. So for example, here we have 2, 6, 18, 54, 162. You can notice here that the pattern is first term 2, the second term is 6, which you can rewrite as 2 times 3. A sub 3, or the third term, 18, you can rewrite that as 2 times 3 times 3. Now if you continue this, you will notice that as the sequence progresses, as the term progresses, you have one ratio for the second term, two common ratios being multiplied to one another, or used as a factor, 3 uses a factor, 4 uses a factor. So the pattern here is n minus 1 because of that. So 5 minus 1, you get 4. 4 minus 1, you get 3. 3 minus 1, you get 2. 2 minus 1, you get 1. Always remember the rule with exponents. If it's not written, if it's just a variable with no exponent indicated, it's automatically 1. Now the formula for geometric sequences in finding the nth term is as simple as a sub n is equal to a sub 1 times r raised to n minus 1. Now you don't have to worry about the formula for the general term. All you have to do is to take note of the first term, which is 2, and the common ratio. In this case, the common ratio is 3. Knowing those two things, all you have to do is to substitute it to the formula, and that's your general term formula already. Okay, so it's 2 times 3 raised to the quantity n minus 1. That's how easy it is. So now let's have another example. We have here, for example, 1, 3, 9, 27, 81. So if you have 3 divided by 1, that's 3. 9 divided by 3, that's 3. 27 divided by 9, that's 3. If you continue, you'll get 3. So that's your common ratio here. So the common ratio is equal to 3. Your first term is 1. So let's list that down. So knowing those two things, you can now actually write your general term formula, since that's the goal for this part of the discussion. So this will be a sub n is equal to a sub 1. Your first term is 1 times your ratio, which is 3, raised to n minus 1. In this case, since you don't necessarily have to write 1 anymore, 1 times whatever the answer is going to be the same thing. So you can actually rewrite this also as a sub n is equal to 3 raised to n minus 1. This only happens if your first term is 1, okay? Next, we have number 2, negative 15 divided by 5, that's negative 3. 45 divided by negative 15, that's negative 3. The common ratio here is negative 3. This is the same example as earlier. So we have r as negative 3, our a sub 1 is 5. So substituting, you'll have a sub n is equal to a sub 1, which is 5. We're going to multiply that to negative 3 raised to n minus 1. Okay, the dot here represents multiplication. Please do not forget about that. Here the pattern is actually 1/2, right? 50 over 100, that's 1/2, or 0.05. So in this case, your answer could be either a sub n is equal to the first term 100, so 100 times 1/2 raised to n minus 1. So you may put a parenthesis here if you want to, and then you can also write this as a sub n is equal to 100 times 0.5 raised to n minus 1. Either way, they're the same thing. You may remove the dot if you want to, because that's going to indicate multiplication. PEMDAS rule, the parenthesis comes first, followed by the exponent. So it's fine. It's going to be the same answer. So that's 1, 2, and 3. Let's have some more example here. Now, in this case, we're trying to find the common ratio. So let's try to indicate that one first. You'll have 3 divided by 1, that's equal to 3. 9 divided by 3, that's also equal to 3. 27 divided by 9, that's also equal to 3. Then 81 divided by 27, that's also equal to 3. Okay, so that's our common ratio. So our first term here, or our a sub 1, is 1. So all you have to do, write the formula. A sub n is equal to 1 times our r here is 3 raised to n minus 1. This is our general term formula. Now, so that it's going to be continuous, we can actually use the general term formula to find the 13th term, which is being asked in this slide. So a sub n is equal to 1 times 3 raised to 13 minus 1. So in this case, you will have a sub n is equal to 1 times 3 raised to 12. Now I think I have to calculator this one, because this is too high for me even. Wait, where's my calcu? I actually don't know where the calculator is in my phone. I rarely use it. How do they call this? How do you do exponents here? What, 3? Bro, they don't have it here. Oh, they have 3 raised to 12. Okay, so a sub 13 is actually 531,441. Now the reason why we skipped this part, like we didn't multiply it anymore, because it's 1. 1 times 531,441 is the same thing. So this is your answer. Okay, next, let's have another one. If you continue this one, we already identified this earlier. Negative 15 divided by 5, you get negative 3. Same thing if you have 45 divided by negative 15, that's negative 3. So I think that's established already. But again, if you want to check everything, you may do that. It's your choice. We're just going to be a little bit faster here. Our first term here is 5. So a sub n is equal to first term 5 times the common ratio, negative 3, raise that to n minus 1. Now we're being asked to find the 12th term. So let's have a sub 12 is equal to 5 times negative 3 raised to 12 minus 1. Now we will have a sub 12 is equal to 5 times negative 3 raised to 11. So what's the answer if you raise negative 3 to 11? Let's see. Negative 3 raised to 11. So the answer here, a sub 12 is equal to 5 times negative 177,147. This is still too high. Times 5. So a sub 12 is equal to negative 885,735. It's too high. Are we correct? Yep, the common ratio is negative 3. So r is negative 3. N is 12. So 12 minus 1, 11. Okay. So this is our answer here. Negative. Next, let's have 150. We already established this earlier. The ratio here is 1 half or zero point 0.5. I'll use zero point 0.5 here because I'm not using a scientific calculator. I'm so sorry. I'm using my phone. So the general term formula is a sub n is equal to the first term, 100, times 0 0.5 raised to n minus 1. We're trying to find the 10th term, so a sub 10 is equal to 100 times 0.5 raised to 10 minus 1. A sub 10 is equal to 100 times 0 0.5 raised to 9. So let's see what the answer will be. 0 0.5 raised to 9. Oh, this is so far. So we'll have 100 times 0 0.00195. So in this case, you can actually simplify it later, because you're going to use your calculator anyway in this thing. But it's important that you know how to substitute so that you will not be confused. So if you multiply 100 to 0 0.5 raised to 9, the answer that we'll get there is 0.1953. Or you may simply put this as 0.20. Again, round up or down when you're done with the solution at the end. Don't do it in the middle. So this is our answer, 0.20. Next, we have here, we're simply finding the specific term given. 3 became 1, 1 became 1/3. The r here is 1/3, it's already given. The first term here is 3. So using the formula for our first one, we're going to have a sub 12. Again, we're double timing here. The 12th term, that's your n. N is equal to 12. So in this case, a sub 12 is equal to, again, substitute that. First term is 3 multiply to 1/3 raised to n minus 1. So raised to 12 minus 1. So let's see where this will lead us. So I don't have a fraction here, so good luck to me. So I have 1 divided by 3. And then I'll raise it. That's how crazy this is. I raise it to 11. Okay, so it's a continuous thing. It's too high. So let me simplify it. 2.33 raised to 11. So it's still going to be a lot of exponents. Then you multiply that to 3. So this is the answer. 0.002, many zeros, by the way. If this is a fraction, I think it's gonna look much better. But there are 4 zeros, then 1 5. This could be 0.00002. You can write it that way. It's complicated. Why did I choose so many fractions as examples? You have here r is equal to 4. First term is 1 over 32. Oh my god, another fraction. So a sub 13 is equal to 1 over 32. Then we will multiply this to the common ratio 4. Why is it not working anymore? Bro, the pen stopped working. Is it low bat? I don't think so. Wait, this is goofy. The pen stopped working. It actually gave up. This is so goofy. Wait lang guys. We're almost done, by the way, for this part. It's 12 a.m. 12 a.m. bruh. Okay, it's back. Finally.
1 over 32, we multiply that to 4 raised to n minus 1. So that's going to be 13 minus 1. So if we simplify that, 4 raised to 12, that's 16 million divided by 32. So the answer here is 524,288. Again, we're speed running this part because again, if you type it that way in your calculator, it's gonna give you the answer quickly. For my end, no, I'm unlucky. The first term here is 30. So a sub 14 is equal to the first term, 30, multiplied to the common ratio, 0.5, raised to n minus 1, which is here, 14 minus 1. So this is 0.5 raised to 13. And then we will multiply that to 30. Okay, so the answer here is, here we go again. It's dying. It's not what. What's wrong with my pen? So goofy. I think it's back now. So this is going to be 0.0036. This could be 0.004. That's the final answer here. So that's how we get the nth term of a geometric sequence. Wow, nice. Now let's continue to our next target. Okay. Maybe we can pause here for a second. Let me take a break. Let me pause this one. But in my case, I can't take a break. I have to finish this one. Ain't no break for the great. But for you guys, you may pause this one right here. Now, in this case, what we're going to continue with is now with regards to geometric mean. So if you wonder what this all means or what it all really mean, there are two things here. We have geometric mean and geometric means. They're two different things. And the first thing is for geometric mean, there's a formula, which is basically the nth root of the product of the n terms. So you have the nth root of the product of n items. Now, this one is not confusing. Don't worry. So basically, for example, you have here 3 and 12, and you're trying to find the geometric mean, the one in between them. So 3 and 12, you get two terms, right? That's your n. Since you have two terms, your n here is equal to 2. When we're talking about product of n items, we're simply multiplying the given 3 and 12. Hence, 3 times 12. That's 36. And the square root of 36, again, if the index is 2, that's square root. Square root of 36, that's 6. Could be negative 6 also. But in this case, in this context, since it's a geometric mean, it must be in between them. It should be positive 6. Okay? Let's have another one. Now, how about for this example? We have 8 and 32. So our n here again is none other than 2. Why is it 2? Because we have two terms. So you have square root of. Now, if the index is 2, n is equal to 2, you don't have to write it anymore. It's your choice. Because square root, from the names of square, that's 2. So square root of 8 times 32. It's going to be square root of 8 times 32. I'm so sleepy. Square root of 256. So if you get that, the answer is 16. So that's the one in between 8 and 32. This is the answer. Next. Oh, geometric mean is 16, bruh. Next one. Now, as you can notice here, oh, sir, there are 4 terms. So what does it mean? 1, 2, 3, 4. N is equal to 4. So we're now looking at the fourth root. Fourth root of 2 times 6 times 54 times 162. Oh my god. How will my phone calculator do this? I don't know. 2 times 6 times 54 times 162. So we're gonna have the fourth root of 104 9 6. Oh god, wait. Is there like a fourth root calculator on Google? Let me do that. Okay. Fourth root of 104976. Okay, it's 18. Thank you so much. It's 18. I just typed it in Google and it gave us the answer. So it's 18. Let's continue. Now, how about if we have 4 and 36? So this will simply be the square root of 4 times 36. What's the answer if you multiply 4 and 36? Wait, where's my calculator? Goodness. 4 times 36. This is equal to the square root of 144. That is 12. Number 2, square root of 5 times 195 is equal to square root of 625. The geometric mean here is 25 if I'm not mistaken. Yeah, it's 25. Now how about here? We will have the cube root. Why is it cube root? Because you have 1, 2, 3 terms. So multiplying them, 7 times 21 times 63. 7 times 21 times 63 is going to be the cube root of 9261. What's the cube root of 9261? Let me search. Cube root 9261. So it's 21. Can you do something for me? So these are your answers for geometric mean. My goodness, I still hope that I'm making sense. Now, let's continue with geometric means. And I wonder if you know what it means. What it means? Bro, this is the last one, I guess, before geometric series. Let's go. Now, the term here is insert, because now it's going to be similar in what we've been doing with arithmetic sequence last time. So there's going to be a lot of terms in between, and you don't have to worry. We're going to maximize simply the formula earlier. So, for example, you have a sub 1 is equal to 2, a sub 5 is equal to 162, and you have the formula, right? So all you have to do is to substitute. Your a sub n is a sub 5, okay? So in this case, you're going to have 162. Again, that's your a sub n. It's your a sub n. Don't worry about it. Now, it's 162 is going to be equal to a sub 1. Your a sub 1 is 2 times r raised to n minus 1. We don't have a ratio given, so it's r raised to, how about the n minus 1 though? That's going to be 5 minus 1. Sir, why is n equal to 5? Because the last term given is the fifth term. Your n is equal to 5. A sub n, a sub 5, 5, n is equal to 5. So if you continue here, we're going to have 162 is equal to 2 times r raised to 4. Now, if you're confused with that, you can actually rewrite this as 162 is equal to 2r raised to 4. Now, what you can do here is to simply manipulate the equation by applying the properties of equality. The division property, you divide both by 2. Why are we dividing both by 2? We want to isolate the variable. So in this case, 2 divided by 2, that's r raised to 4. Now we have 162 divided by 2, you're going to get 81. Now, sir, what do you do here? We want to eliminate the exponent. So you have to eliminate the exponent. So how do you do that? So all you have to do is to get the root of it. The root of it all. But what's going to be the index? Simply the exponent. So you're going to get the fourth root of this example. So the fourth root of r raised to 4 is simply r. So you're just going to cancel it out that way. Now, how about for 81? What's the fourth root of that? It's going to be 3. So your common ratio is 3. Now, sir, what do we do now that we got the r is equal to 3? You can now supply or insert the geometric means. So since your first term is 2, if you multiply that to 3, you're going to get 6. If you multiply that to 3, you're going to get 18. If you multiply that to 3, you're going to get 54. And if you multiply that to 3, you're going to get 162, which is your fifth term. So we're correct. This is your first, second, third, fourth, and fifth. And always remember, when we're talking about the geometric means, it's just 6, 18, 54. So in order for us to get or insert geometric means, all you have to do is to maximize the formula, apply the properties of equality. Mostly what we're going to do here is either dividing both sides by a certain number, by the numerical coefficient, or by multiplication if it's a fraction. So we'll see it here later. Let's have another one. So we have your e raised to 5 ulit. So no problem with that. So we're going to have 81 equal to a sub 1 is 16. Then multiply that to r raised to the quantity 5 minus 1. So 81 is equal to, let's just skip a little here. It's going to be 16r raised to 4. So divide both sides by 16. Again, when you're trying to figure out what to divide both sides with, it's simply the numerical coefficient. This is going to give us 81 over 16 equal to r raised to 4. And just like earlier, get the fourth root of it. So the fourth root of r raised to 4 again is simply r. How about for 81 over 16? So again, we have established earlier that the fourth root of 81 is basically 3. How about for 16? The fourth root of that is 2. So it's going to be 3 over 2. Now, if you want to check that, 3 over 2 times 3 over 2, that's 9 over 4, times 3 over 2, that's 27 over 8, times 3 over 2 is going to be 81 over 16. So that's correct. So the ratio is 3 over 2. Using this ratio, our first term is 16, followed by 24. Yes, am I correct? Is it 24? 16 times 3, 48 divided by 2, 24. Okay. Next one is 36. Next one is 54. The next one is 81. So it's correct. First term, second term, third term, fourth term, fifth term. And this is our geometric means. These things right here. The boxing that I'm doing here, I'm just emphasizing which are the geometric means. You don't have to necessarily do it. You may have the dash lines if you want to. I'm just emphasizing which are the geometric means here that we have inserted. I think we have some more. Yep, negative number. No pressure about that. A sub n, a sub 4. So that's going to be 4 is equal to a sub 1 is negative 32. Then you have r raised to n minus 1. Our n here is 4. So 4 minus 1. So 4 is equal to negative 32 r raised to 3. Divide both sides by negative 32. We're going to get this answer here. Negative 1 over 8 is equal to r raised to 3. Yep, it's correct. So get the cube root of this one. Again, why is it cube root? Because that's the exponent of the variable that we are trying to isolate. So the answer here is negative 1/2 as our common ratio. So our first term is negative 32. Our next one is positive 16. Our next one is negative 8. And our next one is positive 4. So first term, second term, third term, fourth term. So our geometric means is 16 and negative 8. Those are the ones that we have inserted. Now, let's have some more fractions. Bruh. I think this is the last fraction that we're going to use. So we're going to have, I want to show it too, because I want to understand that what makes having a first term and the last term given as both fractions. How do we deal with them? Don't have to worry. So a sub n is 64 over 3. And it's equal to a sub 1 being 1/3 times the common ratio. A sub 3 lang, so 3 minus 1. So no hassle. 3 minus 1. 64 over 3 is equal to 1/3 r squared. So to eliminate the variable here, you can simplify it this way. You can also rewrite this equation as 64 over 3 is equal to r squared over 3. So how did this happen? 1/3 times r squared. So 1 times r squared, you get r squared. Okay. Now, how do you eliminate if there is a denominator? All you have to do is to multiply the entire thing. So let's multiply the entire equation by the denominator so that we can eliminate it. So 64 over 3 times 3, basically you'll get 64. And then r squared over 3 times 3, basically you're gonna get r squared. So it's cancelled out. That's what you do. You multiply the LCD of the given. Again, not all the time will it be as simple as this, depending on the given. Here we simply canceled it all out because they both have the same denominator. Again, this is not true for all. So now we can get the square root because it's r squared. So the answer here is actually 8 as our ratio. So we have 1/3 as our first term, followed by 8 over 3. And if you multiply 8 to this, you're going to get 64 over 3. So that's why it's correct. So the answer here is 8 over 3 only as the geometric mean that we have inserted. That's how you do it. So when you're dealing with these kinds of examples, you just have to take it one step at a time. Again, remember, you have the formula there, maximize it. And in this case, you have to learn how to maximize your calculators, also how you type these things so that you guys will not be confused. So that's it for geometric sequence until geometric means. So we're going to transfer to a different slide because there are some visual examples there. It's hard to transfer to the graduation format, so please forgive me for that. I don't have much time also to edit it out in the graduation background, so don't worry. So basically, we're graduating from this slide. We're going to the next one. So there will be two things that we will discuss here. The first one is finite and the next one is infinite. When we say finite, basically this is the kind of geometric series where there is an ending, hence the word finite. Now, in this case, it is important for us to take note of the formula, which is given right here. S sub n is equal to a sub 1 times the quantity 1 minus r raised to n all over 1 minus r. Please pay attention in the way the formula is presented because this is all you need to do. Maximize the formula and remember what those variables mean. We have the S sub n, which means the sum of the number of terms given or sum of the nth terms given, while a sub 1 means the first term, the r means common ratio, and n is the number of terms. If you know what those variables mean, when you see this formula, you know how to maximize it. And we only use this formula if we're talking about the sum of a finite geometric series. So to continue, let's say that we have this example right here about chain text messages. Funny enough, this is something that is actually super realistic, something that happens. It doesn't go by us at times on how extensive or somewhat how many people receive these chain text messages, even though it just starts with one person. It's like a pyramid scheme of sorts, you know? It starts from one person sending this chain text message and it continues on forever. And for example, right here, you're the one who started it. So you send this chain text message to 3 friends at 7 a.m., thinking that you have 3 friends. Maybe you even have more. Who knows? But then each of them passed the text message to 3 new people within the hour and so on. So basically, the hour that you sent it to them, they already sent it to 3 of their friends. After. That's why after 7 a.m., by 8 a.m., they sent it to 3 of their friends also. Besides you guys, probably. So now, here is the thing that I want to discuss thoroughly. How to create a table for this one. So for example, for 7 a.m., that's our first term, we have right here 3 messages sent. Okay, so that's basically you sending those 3 text messages.
Now, an hour later, again, an hour later, which is 8 a.m., these three people that received your message will send it to another three individually. So here is actually the pattern. That's why you have to pay attention with the word problem. The pattern here now is that the common ratio will become 3, and that will be 9. So 3 times 3 is 9. Where did we get the common ratio? From the statement to 3 new people within the hour and so on. The fact that they passed that one right there. So if from 3 it became 9, the 9 a.m. for the third term, we're going to have 9 times 3, and that is 27. And this will continue as hours go on. So for 10 a.m., that's going to be 27 times 3, 81. Then for 11 a.m., that's 81 times 3, that's 243. And then from 243 in 12 noon, it's going to be 729. And for 1 p.m., 729 times 3, you will get 2187. I hope that one is clear. In order for you to complete a table of values in dealing with geometric series, I'm so sorry. I have to make sure that my voice is clear right here. All you have to do is to take note of the common ratio, and from that example, you will continue in multiplying. So in this case, if you're being asked to get the general term of a given geometric sequence, what you have to do is simply take note of the first term and the common ratio. So the first term right here is 3, and the common ratio is 3. So all you have to do is substitute that to the formula for geometric sequence. Okay, that's how you write the general term formula. So the a sub 1 will be 3, and the ratio will be 3. It's for this example. It's not always 3 all the time, okay? Please take note of that. So if we continue with this one, we can actually get the number of messages that will be sent after 11 hours. Now, this is something that I would like to discuss. Based on the question in here, it says after, meaning to say we are not just considering 11 hours in total, but 12. Why is it 12? Because the word is after. So for example here, your first term is 7 a.m. The first hour hasn't started yet. It starts with 8 a.m. And if you continue counting that, you're gonna have 12 hours in total, okay? Not 11. That's why when the terminology is after, the n here must be 12. I repeat, since the word is after, instead of using 11 for 11 hours, we will use 12. This is only true when, again, the terminology is after. But if the terminology is by or at, it's going to be simply 11. I want to clarify that. So you will have here a sub 12 is equal to 3 times the quantity 3 raised to 12 minus 1. Now, the way that this is presented in here, I hope this one is clear to you guys. It is important for you to take note of and be careful with applications of your formulas or solutions in your calculators. Please make sure, especially when your common ratio is a negative number, to put it inside the parentheses when raising it to an exponent. Because at times, the negative sign is being misinterpreted as a minus sign for some calculators. So you have to be careful with this one. So once we continue, 12 minus 1 is 11. So you will have 3 times the quantity 3 raised to 11, and the answer is 531,441 messages. Again, simply type it in correctly and you will get the correct answer. But always remember, the one that we're showing you here is simply a geometric sequence application because we're not yet asking for the sum or total. So that is where our next question comes in. So the next question here states, how many people received the chain text message after 11 hours? Now, we are being specific as to how many in total received it. We're not just asking you the 11th hour or the 12th hour or so or whatever. We're asking for the total. So for us to get that, what we will use is the formula for a finite geometric series. So we have here S sub n again is equal to a sub 1 times the quantity 1 minus r raised to n, all over 1 minus r. The a sub 1 in this given, again, is 3. So you have to write that down carefully. 3 is your a sub 1. And there, the parenthesis 1 minus r raised to n. Your r here is 3, your n here is 12. Now, we have to be careful here, class. The n there is just n. It's not n minus 1. Be careful. Do not combine two formulas, okay? Stick with whatever the formula is given here. Do not add anything else, okay? At the same time, this one is over 1 minus r. Guys, be careful. It's 1 minus r, not 1 minus n. So this should be 1 minus 3. Okay? So it's important for you to take note that it's supposed to be 1 minus 3 and not 3 minus 1. Changing the sequence of the terms here will change the answer, whether making it positive or whether making it negative. And that will make it wrong. So stick with the way that it is presented. Next. It is important for you to also realize that having the tools with you, the calculators with you, is not enough for you guys to get the correct answer. You have to know how to maximize them. One of the things that I would like to specify is the usage of the parentheses in the numerator. As you can notice here, we have 3 times the quantity 1 minus 3 raised to 12. And that thing right there is inside an open close parenthesis. If your parenthesis is not typed incorrectly, when you have it a small one, basically if you simply have a parenthesis next to the exponent, you're gonna have a math error in your calculators. Make sure that the open and close parentheses that you have are of the same style or measurement. I hope you guys are getting what I'm trying to say here. If you type it in your calculators in the wrong way, you're gonna have a small parenthesis on the other side. So you have to be careful with that. And when you put this in, your answer is going to be 797,160. Hence, that is the amount of people who's gonna receive that chain text message after 11 hours. And once again, since the word is after, we use n equal to 12. But if the terminology is by or at, we're gonna use 11 as it is. So that's the clarification here. So you may try on your own getting the number of texts that will be sent, or people, the amount of people that will receive the text message by 11 hours or at 11 hours. So you may check that one out for yourself to practice. Now let's have another example. So here we have the Paolo and JC, and they plan to have a vacation getaway next year by the end of April. They start saving this month, which is September, for example, and expect the vacation to cost $1,775. They start with $120, and each month they plan to deposit $20 more than the previous month. Will they have enough money for their trip? Now, in this case, we will use finite geometric series again because there is an ending. What's the ending? It will end by April. So in this case, if we continue with the solution, we can identify the first term as stated in there. They start with 120. That's your first term. Next, the common ratio here is also stated, but in a more complicated manner compared to the previous example. It states here that it is 20% more than the previous month. Now, to make this clear, the terminologies here are important for you to take note of. It's not basically 0.20 for the ratio. It's going to be 1.2. Now, you might be asking why. In here, we use 20%, and after that, we use the terminology more than. If you convert that into an operation in mathematics, that means addition. So how did it become 1.2? So 20% is added to the percentage of the previous month, which is 100%. Altogether, that will be 120%. And if you convert 120% into decimals, it's going to be 1.2. And that's it. That's why the ratio is 1.2. And now that we have the first term and the common ratio, now what we have to do is to count accurately with the number of months. If they start with September, that's your first term. September, October, November, December, January, February, March, April. That's going to be 8 months in total. Hence, your n is equal to 8. That's from September to April. And now that you have these three terms, a sub 1 as 120, r as 1.2, and n as 8, you can now answer the sum of this finite geometric series for us to find out if they will have enough money for their trip. So by substitution, again, you have to be careful with this. And then if you substitute it correctly, you're gonna get the answer 1979.89. Disclaimer, the answer right here is estimated. So what my suggestion here is this, and please do this also. You can only do rounding off, or I suggest that you do rounding off at the end of the solution. Do not round off or estimate in the middle of the solution. So if you continue with the substitution part, there's nothing wrong with that. Continue with it. And then afterwards, you're going to get an answer with a lot of decimals, not just 1979. So that's where you round off or you estimate things, okay? That's where you do it at the final answer. And in this case, when you're answering a word problem, don't just give the value or the, what do you call this, the digits. Give also the answer to the question. The question is that, will they have enough money for their trip? The answer is yes, because their goal is simply 1,775. But if they will continue with this kind of progression, they will actually have more money than expected. So you have to be like that, okay? You have to answer the word problem in total. So these are our examples for a finite geometric series. So what makes this different with an infinite geometric series? Well, before we go there, please try this out on your own. Number one, number two, and number three. I think I didn't expect that there's another slide, but here's the thing. So that you can practice this on your own, I will actually give you the answers. These are the answers for numbers 1 to 3. Number 3, the reason why the symbol is like that, because the answer again is estimated. Okay, it is rounded off. So what I want you to try on your own now is to identify the first term, the common ratio, and the number of terms, and check if you will be able to get the answers correctly. Again, the ones on your screen right now are the correct answers. Those are your given. Substitute correctly. Now, this is something that I would like to address now because it's hard to go to the previous slides later on. The reason why this is finite is because the terminologies first 10 terms, first 15 terms, and first 12 terms are mentioned. Hence, there is a limit. There's a clear beginning and there's a clear ending for this finite geometric series. Okay? Because that will be different now that we are in infinite geometric series. Now, to put this into context, we're not going to dive in deep with the complicated explanations, but why don't we try and identify what makes a convergent and divergent infinite geometric series? This is something that we cannot focus on. Why? Divergent is basically an infinite geometric series with no clear ending. So ito yung walang clear ending. Ito yung forever. Something that you guys cannot relate to probably. Who knows? But anyway, my point is, for example, 1, 2, 4, 8, 16. This is gonna continue forever to positive infinity. Okay? Wala siyang ending. We cannot find the sum of that. While for convergent, this is a bit different. You have here, for example, 64, 32, 16, 8, 4. This one right here is going to approach a certain value. That's why there is an inequality posted in there that the absolute value of the ratio must be greater than 0 but less than 1. Okay? In some cases, to put this in a much easier manner, the answer for the common ratio should be a fraction less than 1 if you get its absolute value. Kunyari, negative 1/3. The absolute value of that is 1/3. That's less than 1 and greater than 0. That's the meaning of the inequality right there. Okay? So that's the pattern. So for example, 64, 32, 16, 8, 4, if you continue multiplying 1/2 to the values to get the next terms, it's going to be a smaller and smaller and smaller and smaller decimal until it gets closer to 0. It will not be 0 though. It will not be 0, but it will be closer and closer to 0. That's why it's still considered infinite. So imagine this, guys, like two numbers, 1 and 2. There are infinite numbers between them, okay? But we know that it approaches 1 or it approaches 2. That's the concept of an infinite geometric series that we can actually measure. That's why there is a formula where we have a sub 1 divided by 1 minus r. So here is what I want you guys to understand. In the first examples that we had in this part of the lesson, we have a certain number of terms being mentioned. There is a limit. There is an ending to what we wish to measure. But in this case, for a convergent infinite geometric series, there is still no ending, but there is an approaching that is being done, a value that's being approached. And there is no number of terms being mentioned because we will never be able to find the number of terms of infinity. That's why it's infinity. It cannot be counted. But in this case, we can get the partial sum because of the formula we have here. A sub 1 divided by 1 minus r. So let's try to apply that one right here. So let's say that we have this word problem about a swinging pendulum. A pendulum swings 3/4 the distance of its previous swing. If its first swing is 30 centimeters long, find the total distance traveled by the pendulum before stopping. So one of the things that we have to hit here is also the maximizing of a table of values. So let's try to do that first. So for example, we start with the first term, meaning the first term here is the first swing. And as mentioned in the word problem, if its first swing is 30 centimeters long, so it should be 30 centimeters. Now, how do we get the second swing? All you have to do is to use the common ratio, which is 3/4, and multiply that to 30. So 30 times 3/4 is going to be 90/4, or in decimals, that is 22.5. So what happens next? In order to get the third swing, what you will do is use the common ratio again, and this time around, multiply it to 22.5. The answer will be 16.875. And this is going to continue until you fill out your entire table. Now, I have to, again, maximize this part of the discussion. Do not hesitate to keep multiplying. That's the process of geometric sequence or series anyway. You multiply the common ratio to the terms in order to get the next ones, right? We don't add here, we multiply. You have to be careful. Now, for the concept of a scatter plot, we're gonna maximize this next term, but the idea is simple. All you have to do is to partners the number of swings and the distance. The number of swings is your x and the distance is your y, so it's gonna look like that. Now, this is an application of the Cartesian coordinate system or the Cartesian coordinate plane, and basically it's not that difficult, okay? So 1 is your x, your 30 centimeters is your y, so you can plot that on the graph. Now, in this case, let us now focus on what we can manage for and what is our focus in the first place. Now, to answer the question, what is the total distance traveled by the pendulum before stopping? This is again our formula for a converging geometric series. A sub 1 all over 1 minus r. Your a sub 1 here is 30. So have 30 as your numerator. Again, how did we know that a sub 1 is 30? It is stated in there. The first swing is 30 centimeters. And then 1 minus r. Your r is 3/4. So 1 minus 3/4, you can do that manually. That's 1/4. So 30 divided by 1/4, you're going to get 120. Meaning to say the answer to this word problem is that the pendulum travels 120 centimeters before stopping. As easy as that. Okay? So again, when dealing with word problems, remember, there is no specific end term being mentioned in word problems involving infinite geometric series that are converging. Okay? While in finite, the number of terms is being mentioned. Okay? Do not, again, mix the formulas. That's the clue, the one that I just mentioned. So in this case, we can also have our last word problem right here, where we're going to deal with a bouncing ball. So a ball dropped from a height of 4 meters rebounds to 40% of its previous height. Find the total distance traveled by the ball. Now, I would like to make a disclaimer. That's why we have the letter C question in here. We are not going to measure the entire distance traveled by the ball in terms of the upwards and downwards motion of it. Instead, we are going only for the vertical distance. So how is that going to be translated in here? So as stated in the word problem, we start at 4 meters. Here we have Pichu and the Pokeball, for example. So we start at 4 meters when the Pokeball dropped. That's our start. Now, how do we get, in order for us to draw a diagram or a table showing the distance traveled? Use our common ratio. The common ratio here states that it's 40% of its previous height. Now, disclaimer to everyone, do not mix in the use of percent that you're going to add it to 100 automatically. No. Earlier, there were terms used such as more than. That's why we added 20% with 100%. In the case of this word problem, there is no such mention. We are just focusing with 40%. Okay? Hence, that is automatically your common ratio. Now, we don't use percent as our common ratio in this concept. So what you have to do is to transform it to decimal. If you're finding it confusing, how do you transform a percent into a decimal? Divide it by 100. Or you may move the percent, the, what do you call that? The dot, which is it basically after every whole number. And if you move that to two places, it's going to be zero point 0.4, just like that. I'm so sorry, I forgot how to explain it in elementary way. Yeah, it's really, really far, but you have to double check on that one. So you multiply 4 to zero point 0.4 because it's your common ratio. You're going to be able to get the next measurement, which is 1.6. Again, 4 times 0 0.4 is 1.6. If this continues, the next vertical distance is going to be 0.64. And if this is going to continue, it's going to be 0.256. Again, what's happening here is we're multiplying each term to zero point 0.4 to get the next term. Now, 0.256 times 0.4, you're going to get 0.1024. And again, this is going to continue endlessly until it reaches the point that it's closest to zero. It's not going to be zero, but it's going to be close to it. So now, as a way for you guys to conclude this concept, I'm giving you guys the chance to work on this one using the formula for an infinite geometric series, which is S sub n is equal to a sub 1 all over 1 minus r. So just to make sure, you can pause this part so you could solve for it on your own, and then I'll just basically blatantly mention the answer because it's important for you guys to practice this one. The first term is mentioned in the word problem, and the common ratio is already mentioned. All you have to do is to substitute properly. Well, I guess we're back. So all you have to do there, it's going to be 4 divided by 1 minus 0 0.4. And if you continue with that solution, if I'm not mistaken, the answer here is, wait, let me double check with my calculator. 4 divided by 0.6? Yeah. So this is going to be 6.6666666 and continues like that way. So what you can do is to simply put it as 6.67. That's the total measurement or distance traveled by the ball while it bounces vertically. Oh, sorry. The total vertical distance traveled of the ball vertically. So that's it. So that's how you answer those kinds of examples. And that basically ends our discussion for an infinite geometric series and a finite geometric series. And that ends this video for geometric sequence and series. I hope you guys were able to check or review the parts that you had troubles answering. Hopefully this one really helped. Hopefully, I don't know. Good luck with that. Nobody watches this part anyway. Even Garfield doesn't want any part of this anymore. Right, Garfield? Homie, I have 7 lives left. Why are you bothering me? I'm just kidding. He's gonna get his lasagna. But anyway, good luck with your exams, your lessons, whatever you are preparing for. Now, I hope I can try to make the videos next time more advanced, because actually I have the presentations and some of them prepared already. But sometimes, I feel sleepy. A lot is happening lately. I'm just gonna say that, and I have to work on things too. So maybe I'll promote them. Who knows? I have to. I have to promote my other ventures sometimes, you know. But anyway, hopefully this one reaches those people who needs to be reached at this moment in time. Good luck with that. And again, always remember what's up. That's respect. And in case you don't see me, good morning, good afternoon, good evening, and good night. Bye bye. Peace out, bruh.